record our session, and I'm going to go ahead and click that record button right now. And as far as that control panel, you see where there's an orange arrow, an orange rectangle with a white arrow in it?
No.
On the upper left of the control panel.
I don't think I see it.
All right, not important. That's a toggle switch that lets you minimize or maximize the control panel, but you really don't need that control panel anymore. In other words, everything we do, we can do. The way I usually do this is you can verbalize problems to me. I'll write the problems, and then we'll solve them together.
All right.
Okay? So what kind of stuff are you going over now?
I don't have pre-calc until my spring semester, so I haven't started it yet, except for what I did with my last tutor.
Okay. So do you have some problems you want to discuss?
Most of the things we did together, we ended, but we went over like logarithm, some equation.
Okay.
We went over the quadratic formula.
Uh-huh.
She did a lot of algebra 2 with me as well.
Okay.
Although I already took that.
The way I usually work is I ask the student to bring problems to the table, and then we go over problems. Because obviously I want to go over whatever you're going over in class right now. And pre-calc is pretty broad. You're not in trig right now, are you?
No.
Okay. Are you taking pre-calc trig or just pre-calc this year?
I'm just going to be taking pre-calc.
Okay. Okay. And so far you've just been reviewing Algebra 2 stuff?
Yeah, just with my last tutor.
Okay. Okay. So what do you have in the way of problems that you'd like to look at?
Logarithms still kind of confuse me.
All right. Let me give you my basic Log 101 class. If all discussions on logarithms start out with this, that's an exponential function. Notice that my variable is in the exponent. Significantly different than if I had this. This is an algebraic expression. My variable is on the algebra line. Completely different if I write y equal 2 to the x. That is an exponential expression. So the very, very first thing you need to know about logarithms is how to write an exponential expression as a logarithmic expression. Do you know how? In other words, an example of this might be 8 equals 2 cubed. How would you write both this and this logarithmically? You only have to memorize one thing. Logs are exponents. Okay? So if I'm going to write that logarithmically, I can start off immediately saying logs are exponents. Well, that's the exponent right there, x. Now, where does the b and the y go?
With the y go next to the log and then the b go next to that.
Yeah, the b always goes down there, right? Which leaves that as the only place to put the y. Okay? So these two expressions are the same thing. And you want to be able to interchange them. You want to go back and forth. The whole secret of logarithms is to be able to go back and forth between these two expressions. So how would I express this logarithmically? 8 equals 2 cubed. How would I express that logarithmically? Log, and always start out your log equation by that?
Would it be log under script?
Yeah, I usually say that log base what? What's the base?
2.
And what's the argument?
8.
And we know logs are exponents, so the exponent has to go over there. Now, if you're going the other way, if you have a logarithmic expression and you're trying to express it exponentially, kind of the way I memorize it is it's the number on the far left raised to the exponent of the number on the far right, and that's equal to the number in the middle. In other words, 2 cubed equals 8. So these two are identical as those two are. So this is the very first rule you need to deal with logs, is to be able to go back and forth between the exponential expression and the logarithmic expression. Okay. Express that logarithmically.
Would that be log base 3, 27 equals 3?
Yeah. Okay. And express this exponentially. What's the base of natural log?
Would it be automatically 10?
No, it's this. The base is, the reason it's written natural log is because its base is e, the number e. In other words, I could write this also like this. Log base e of 10 equals x. So how would you express that exponentially?
It would be 10 equals e to the x power.
Yeah. All right. So that's the basis of logs. Now, there's a couple of other things with regards to logs that you really need to know. And I'm going to label them. Let's talk about the log of a times b. In other words, and it doesn't matter what the base is. The base can be 10, it can be e, it can be 7, it doesn't matter. As long as my base is the same, then I can say that that's equal to what?
10?
It's equal to the log of a plus the log of b, regardless of the base. Okay?
Okay.
Second rule, if you're dividing in the argument, in other words, a divided by b, what do you think that would be?
Would it be log a minus log b?
Yeah. And finally, there's a very important third rule that says if you have the log of a raised to the b, what is that equal to?
Isn't it equal to b log a?
Yeah, in other words, it turns into multiplication. Notice that up here we have multiplying going on, and it turns into addition. Here we have division, turns into subtraction. Well, here we have exponentiation, and the next lowest thing below exponentiation is multiplication. So you can kind of remember these by they're very similar rules to the rules we had with exponents, as they should be. In other words, if you'll remember exponents, if you had x to the a times x to the b, what's that equal to?
That would be log a.
No, we don't have any logs yet.
Oh, it would just be.
Yeah, in other words, if I had, say, 2 cubed times 2 to the 4th, how do I do that problem? What's that equal to?
2 to the 7th power.
Yeah. In other words, when I'm doing multiplication, I am adding the exponents. So the rules for logs are exactly the same as the rules for exponents. When you're doing multiplication, you add. When you're doing division, you subtract. And when you're doing exponentiation, you multiply. All right. Now, there's a couple of other things that are very handy when it comes to logs to know. And so let's make this. What is the log base b of 1 equal to? The log of 1 is always equal to 0, regardless of the base. Why? Because b to the 0th power is equal to 1, regardless of what b is. In other words, any number raised to the 0th power is equal to 1. It doesn't matter if it's 1,000,000 raised to the 0th power or 0 raised to the 0th power. They are all equal to 1. So that's why I can make this statement, is because b to the 0th power, regardless of what b is equal to 1. So log of 1 is always 0. And finally, if I have the log of b, in other words, if I'm taking, what's that going to be equal to, regardless of what b is?
It's going to be just 0.
1.
Or 1.
In other words, b raised to the 1 power is equal to b, always. And it doesn't matter, once again, what b is. So these 5 rules for logs are absolutely vital that you memorize these. Those 3 and these, you can kind of figure these out once you get used to working with logs. But whenever you see the log of x is equal to 0, you know that it has to be 1. Or if I said to you, what is the natural log of e? What's that equal to?
Natural log of e is equal to, is it just e?
No. What's the base of natural log?
It's e, so it'd be...
Yeah. So that's got to be 1. In other words, e is just a number. It's 2.71 and change. So when I say the natural log of e, I'm saying the log base e of e, and that's this situation here, and so it's always 1. All right. Now, these 5 rules are pretty much, what's this equal to?
Zero?
No, it's not defined. In other words, you can only take logs of positive numbers. You cannot take logs of negative numbers, and you cannot take logs of 0. Notice that there is nothing that I can put over there that if I took any number and raised it to that power that I would get 0. You can't produce 0 when you do an exponential function, which means this is impossible. So the domain on the log function, let's talk about domain for a moment. If I said this, what's the domain of that? What does x have to be?
It would have to be square root of y squared.
It's got to be greater than or equal to 0, right?
Yeah.
In other words, I can't take the square root of negative numbers, but I can take the square root of 0. So the domain on this function is x's that are greater than or equal to 0, but if I have this function over here, that is a more restrictive domain. That has to be greater than 0. It cannot even be equal to 0. So that becomes of vital importance on logs, because when you get into solving logarithmic equations, you sometimes can come up with answers that'll give you a positive and a negative, and you have to throw out the negative. In other words, it has to be in the domain, and the domain is positive numbers only. Now, now that we've gotten into it a little bit, do you have any problems you can draw on that you'd like to solve, or do you want me to look up and find some?
You can just look up some problems, I guess.
Okay. Let me see what I've got in my... All right, let's take a look at this. Let's first of all look at the top. I apologize for the bleariness of this. Hopefully you can read it, and if you can't, I'll write it. So what we have here is, can't even read it myself, what that is there.
Is that a S?
It sure looks like it. Okay, we'll call it an S. So we got all right, they want us to condense this. Now, notice if we go back to our first 3 rules, these 3 rules here, you want to be able to go both ways. If I'm expanding, I'm going in this direction. If I am condensing, I am going in this direction. Okay? Well, if we look at this problem, we've already got it separated into 2 logs. So we must be going the other way. We must be condensing. And we're going to need to use rules 3 and 1. Let's use rule 3 first. What does 4 log s become using rule 3?
Log s to the 4th power.
So I'm going to replace this with log s to the 4th. And what's the next term become?
Log y to the 3rd power.
Now use rule 1 to put them together into a single log function.
It would be log s to the fourth power multiplied by log y to the third power.
Exactly. And you're going to get these in both ways. In other words, they may give you that to start with and you have to expand it, or they may give you this to start with and you have to condense it. Okay, so that's the two things that you really need to be able to do with logs. So let's condense this one here. I don't know if you can read that or not. It is log, and you can only apply these rules if the base is the same. In other words, if this were log base 2 and this were log base 3, it would not be able to combine these things. But as long as it's all base 2, then I can do it. So what's the first thing I want to do?
You're going to want to make the second part log to the base of 2 to the 4 to the half power.
Like that. Okay.
And then you want to do log base 2, 18 divided by 4 to the half power.
And that is square root, that's 2. In other words, the square root of 4 is 2. And so that's the same as the log base 2 of 9. Now, you might say, well, what happened to the square root of 4 being minus 2 also? Which it is. But if I use the minus 2, I end up with a negative argument. So I throw it out, and I only use the positive 2. Okay. Let's solve some exponential equations. It's the first step.
Add 17 to both sides.
Second step.
Divide both sides by 5.
Third step. This is where it gets tough, right? Because this is not an algebraic equation. That is an exponential equation. We don't have algebra to solve that. There's no algebraic way to solve this problem. But you can solve it using logarithms. Okay? The way you solve it using logarithms is to take the log of both sides. Well, what kind of log? I can take the log base 2 of both sides. I can take the log base 1,000,000 of both sides. But the best log to use is base e. In other words, I want to take the natural log of both sides. The reason being is, what's the natural log of e equal to?
E equals 0.
It's 1. In other words, whenever this base is the same as this argument, you can replace that with a 1. And I can also, first of all, bring the 12x down in front. So it's really 12x times the natural log of e, which is equal to the natural log of 8. And now I can replace natural log of e with the number 1. So I have 12x equals natural log of 8, which means x equals natural log of 8 divided by 12. And that is the best answer. You don't want to turn that into an approximation. In other words, you don't really want to look up on your calculator and figure out what the natural log of 8 is and round it off to 3 decimals and put it in there. It's kind of like whether you choose to write pi or 3.14. It doesn't matter. If I'm writing it as a decimal, it's an approximation. So the most accurate representation of the number pi is that. Same thing with square root of 2. I can approximate it by writing 1.41, but it has decimals going out to infinity. So you don't write it as a decimal, you write it as square root of 2. Same thing with logs. That's a number. You can get that out of your calculator. In other words, what kind of calculator do you use?
I have a TX88, I think.
Okay, a TI? It's not a... Okay. It's not,
Yeah,
it's not a TI-84 or?
I think it might be. I know it's TI-80 something.
Okay. It's a graphing calculator?
No.
Oh, it's not. Okay. But you can get logarithms on this. In other words, the only way I have of coming up with that number right there is to look it up in a table or go to a calculator and get it. Okay? In other words, at one point in time, before calculators were ubiquitous, all math books had tables. They had log tables and natural log tables. So if you wanted to know what the natural log of 8 was, you had to go to a table and look it up and then write down the approximate decimal that it equals. All right, let's look at 19. Is this close to what you've been doing?
With my old tutor, yeah.
Okay. First step?
Subtract 1.
Subtract 1 and then divide by 2. So I'll do both steps at once.
Then you raise each side to a natural log.
Uh-huh.
And then it would equal x to a natural log 2.
And there's your answer. E to the x equal 12. First step?
Raise each side to the natural log.
Yeah, it's not raising each side. It's taking the natural log of each side. In other words, with equations, you can do anything you want to one side as long as you do it to the other, and I mean anything. You can add numbers, subtract numbers, multiply, divide, take logs of both sides, take derivatives of both sides. You may not know what a derivative is yet, but it's coming in calculus. And you can take integrals of both sides. So what I'm going to do is I'm going to take the log of the left side, which means I have to take the log of the right side also. So what's x equal to?
Natural log 12.
All right. Let's skip over here to 22. Here we have 2 to the x, another exponential equation, not algebraic. We don't have an algebraic way to solve this.
Would it be...
You can always work with natural log, even if the base is not e. In other words, let's use natural log. We're going to do this a couple of ways. First time, let's use natural log. Once you get into calculus, you realize that natural log is what everybody uses, and you don't use much else besides natural log. Well, now this allows me to bring the x down there, so I have x natural log of 2 equals natural log of 12. So when I solve it, I have x equal natural log of 12 divided by natural log of 2. And that's the answer. Okay? There is another way to do this problem, and most people would choose to do it this other way, which would be, instead of taking the natural log of both sides, they would take the log base 2 of both sides. And the advantage of taking the log base 2 of the left side is it reduces it instantly to x, because that's always 1. If this is the same as that, then this thing is 1, so it's x times 1. So I have x equals log base 2 of 12. That is the answer also. But do you know the change of base formula?
The what formula?
It's called the change of base.
No.
If I have the log of A base B, it's always equal to the log of A divided by the log of B. The log of the bigger number, shouldn't even say that, the log of A divided by the log of B. So if I want to get that number out of your calculator doesn't have a log base 2 on it. Your calculator only has 2 keys. That's a log base 10, which is called common log, or a natural log, which is base E. So for me to convert this to a number, I would have to say it's the log of 12 divided by the log of 2. Well, that's the same answer we got when we did it the other way. We got the natural log of 12 divided by the natural log of 2. Well, guess what? Those two things are the same. In other words, all of these are the same. The log of 12 divided by the log of 2, and that's presumed to be common log, base 10, is the same ratio as the natural log of 12 divided by the natural log of 2. It's also the same ratio as the log base 2 of 12 divided by the log base 2 of 2. In other words, when you're looking at ratios, all of these log ratios are the same, even though all 3 of them have different bases. So when you're talking about the change of base formula, in other words, if I'm taking that, well, I'm going to say it's the log base 12 over the log base 2, and I can make that anything I want. I can make B 10, I can make B E, I can make B 17, I can do anything I want with it. So I don't even think of that as something to remember. When I'm trying to memorize the change of base formula, I remember it as the log of the biggest number, the biggest size, and I don't mean 12 being bigger than 2. I mean, it's the log of the argument divided by the log of the base. All right. So either way I do that problem 22, I get the same answer. So it doesn't matter. About this. 6 to the point 1x plus 5 equals 10. First step?
Subtract 5 from this one.
6 to the point 1x equal 5. Next step?
Then you'll take the natural log of 6.
Yeah, I would use natural log. Some people might be inclined to use log base 6, but you can kind of see that it doesn't really make it faster, because we are not going to have to use the change of base formula the way we're doing it. Whereas if you did log base 6, you would have to use change of base formula. Now, what's the next step? What's the next line? Always to get this onto the algebra line. If we can get the variable out of the exponent, then we have an algebra equation that we can solve. Well, remember rule 3? Rule 3 was you can always take that exponent and stick it in front. So I can rewrite this left side as 0.1x natural log of 6 equals natural log of 5. Now what?
You would divide both sides by natural log 6.
Okay. So that gives me that. Now what?
And then you divide, or multiply both sides by 10.
Okay, same as dividing both sides by 0.1. So I can put a 0.1 right there. Okay. Now, notice that everything on the right side is a number. That's a number I can get out of my calculator. That's 0.1, and that's a number I can get out of my calculator. So I have solved it. And this is the best answer. I mean, maybe it's not as good as putting that 0.1 up here, 10. That might look a little prettier than dividing by 0.1. But that's my final answer. 10 natural log of 5 divided by natural log of 6. Okay. Let's do this one real quick. I'll go ahead and add
You would take the natural log from each side. Then you do x natural log 4.
So x ends up being natural log of 8 divided by natural log of 4. And it's important not to get that confused with rule 2. In other words, if I had natural log of 8/4, that would be the natural log of 8 minus the natural log of 4. But that's not what we have. We have natural log of 8 divided by natural log of 4. There's no way to expand or compress that. And yet it's an easy mistake to make. In other words, these 3 rules only apply to when you are multiplying or dividing. Notice, that's just multiplication. There's no rule for log of A divided by log of B. That's not on this list anywhere, which means it can't be simplified. If you have multiplication going on inside the argument, then you can separate it into 2 log functions. But only then. In other words, if I write the log of A divided by the log of B, that's not on these 3 rules. That is not simplifiable. That would be the final answer there. All right. We've got about 15 minutes. We can stay on logs and do more log problems, or go to something different if you like.
Okay. We can just go on to something different, I guess.
Well, what would that be? Tell me what subject. In other words, precalculus is pretty broad. There's a lot going on in pre-calc, so I'm not going to pretend to know what comes next in your curriculum. You're in Pennsylvania, is that right?
Yeah.
They have Common Core there, don't they?
Yeah.
Yeah, I'm in Colorado, so your pre-calc course in Pennsylvania should be very similar to the pre-calc courses here in Colorado. So I should have a pretty good feel for whatever you're working on. Let me get my pre-calc book out. Let's see what goes with logs, or what comes next. Have you had third degree equations yet? Cubics?
No.
No? So you haven't had things like the rational factor theorem?
No.
Okay. Well, my pre-calc, 10 basic functions and transformations of those functions. You doing anything like that?
I don't actually have pre-calc yet. My school has the spring and fall semester system, and I currently don't have pre-calc in my schedule until the spring.
Oh, okay. So you're still doing Algebra 2 pretty much.
No, I took Algebra 2 last year, my freshman year, so I don't have a math until about mid-January.
Oh, so you're not taking any math at all now?
Not yet.
Okay, I gotcha. So you're in between Algebra 2 and pre-calc. All right. Let's do more logarithms, merely because they can get a little bit more complicated, and you can get into logarithmic equations and solving logarithmic equations, and those can be a little tricky. Let me see if I can find some. Hold on. Well, let me see if I can make one up here. If I say the common log of 100 plus the common log of 1 equals 2. No, hold on a moment. Equals x. Let me look at my book and see if I can find some. In fact, let me look on this piece of paper here. I might have some log equations here. Hold on a moment. these are, we just did those. These are the same. 21's a little different. Hold on a second. Let me do a better job of making this problem up here. If I have the log of x plus the log of, in fact, let's make it x plus 1 times the log of x minus 1. And that is going to equal 3. Let's see if we can solve for x. And the fact that I have not specified a base means it's 10. So what's the first step I want to do to solve this logarithmic equation?
Would it be to do log x plus 1 multiplied by x minus 1?
Which is x squared minus 1, right?
Mm-hmm.
Okay. Now what?
Then...
Now, the way you solve logarithmic equations is at some point near the last step is you convert it to an exponential equation. So how would I convert that to an exponential equation?
Would you first separate them by doing? Well,
no. In other words, if I'm going to try to express this logarithmic equation exponentially, then that's the base, 10. So I'm going to go 10 to the third equals x squared minus 1. In other words, the number on the far left raised to the power of the number on the far right equals the argument. Now I have something I can solve. In other words, I don't have it in logs anymore. I've got 1,000 equals x squared minus 1. So x equals plus or minus the square root of 1,001. So that's my solution. Problem is if I go back to the original problem, which was this, notice that the negative solution doesn't work. When x is the negative square root of 1,001, then both of these arguments turn negative, and you cannot take the log of negative numbers. So we go to that part of the answer and we throw it out. We erase the negative, and we're only going to deal with the positive solution. So that's the final solution. And that's very common with logs. You very, very frequently, when you're solving log equations, you'll come up with a plus and a minus. It turns into quadratic quite easily. And so quadratics generally have two solutions, plus and a minus. And the minus solution will frequently violate the domain. Sometimes the plus solution will violate the domain. You know, if I'm taking the log of negative x, then I need x to be a negative number. So it's not always just the negative solution that you throw out. It's whatever solution turns the argument negative. Now, notice one thing here that's very important. Had I tried both solutions and plugged them into that, my argument is positive with either solution, right? Because I'm squaring the x. But just because it passes the domain test on this step, you can't test the domain on that step. You have to go back to the original step. these two things are not precisely the same. I mean, we've been talking about them for an hour now, and we've been acting like they're exactly the same, but they're not really. You can have a domain of x, anything greater than 1 or less than -1, and this would still pass the domain test. But if you go back to the original, you have to have an x that is greater than 1. That's the only thing that passes both of these domain qualifications. And this is something that's a little hard to understand because we're taught that these two things are equivalent, but domain-wise, they are not equivalent. This requires an x greater than 1, whereas this would require a negative x is okay because I'm squaring it. All right, let's see. Let's do one more of these, and then we'll be about out of time. I'm working with you for an hour, and then your brother for an hour. Is that right? Okay. Is he going to be on the same computer or a different computer?
I think he's going to be on the same one.
Okay, good. So he won't have to re-download Gotomeeting. Okay. How would we solve this?
You would take a natural log of both sides.
Next line.
Then you do x plus 5 natural log 2.
You do need the parentheses there.
Then you divide both sides by natural log 2. And then subtract 5.
And that's your answer. And that's as simplified as we can make it. Okay. All right. Can you expand 17? I think this is an expand, yeah. Log base 2 of 5 root x. First of all, notice that we're doing multiplication there. That's 5 times square root of x. So,
oh, okay.
So
you would do log.
Go ahead.
You would do log base 2 5 plus log square root 5 or x.
Correct. And it's best to turn radical signs into fractional exponents. In other words, instead of square root of x, I'm going to say x to the 1/2. Because now I can expand it all the way. Now I got log base 2 of 5 plus 1/2 log base 2 of x. So that's the full expansion. Yeah, radical signs don't play very well with logs. You want to pretty much convert square roots and cube roots to fractional exponents so that you can take that exponent and put it down on the algebra line. All right. Isa, is that how you pronounce your name, Isa?
Yep.
Okay. Is your brother there with you, or?
No, I have to go grab him.
Okay, you want to do that, and I'll just stay on this meeting, and he and I can pick up where you and I left off.
Okay.
Hello.
Hello. And what's your name?
I'm Saad.
Saad. My name's David Cowan.
Okay, hi, nice to meet you.
Nice to meet you. And this is the platform I use for doing online tutoring. It's a Gotomeeting software, which your sister downloaded and installed on that computer. And I have a drawing tablet hooked up to my computer so that whatever I write, you should be able to see or draw. You can see all of that, okay?
Yep.
Okay. And you're taking Calc AB?
Yeah.
AP Calc AB?
Yeah.
Okay. And you've just been in class for a couple weeks now?
I think it's been 2 weeks now, yeah.
Okay. So what'd you take last year? Did you take pre-calc trig?
It was just called Precalc Honors.
Did you have trig?
Yeah, we did a little.
Okay. Because trig is pretty fundamental to calculus also.
Yeah.
Where are you at in calculus right now? Are you on limits? Are you on differentiation? Are you on the rules, the product rule, quotient rule, all of that?
We just started continuation today, or continuous.
Continuous functions? Okay.
Yeah.
Do you have any material that you'd like to go over specifically?
I guess like, how to tell if it's like a hole or an asymptote or the break. I forget what was the other one, the third.
Okay. Let's look.
Just how to know how to identify it.
Let's look at this function right here.
Okay.
How would I graph that?
There'd be a hole at 1.
Okay, what's the first thing I would do? You're right, there's a hole at 1, but why is it a hole and not a vertical asymptote? In other words, if this were the problem, it wouldn't be a hole at 1. It would be a vertical asymptote, right? Whatever makes the denominator 0 ends up being a vertical asymptote. The difference is that I can factor the top. What's the fact? That's difference of perfect squares. How does that factor?
X plus 1 and x minus 1.
Now that x minus 1 cancels out with the bottom.
Mm-hmm.
So this function turns into x plus 1 with no asymptotes. But you can never forget the fact that if you're starting there, then x can never be 1, regardless of whether I can factor the top and cancel the top with the bottom or not. That domain restriction, that x cannot be equal to 1, has to carry forward even to this. So my answer is not really x plus 1, it's x plus 1 with the provision that x cannot be equal to 1. And that provision is what puts a hole there. In other words, if I graph that, that's basically a line like that, and I would have a hole there.
Okay.
And incidentally, if you graph these on your calculator, what kind of calculator do you use, Sai?
Right now I have a Casio, but I'm gonna get the TI-85 one, whatever that's called.
Probably it's the Inspire. In other words, the latest and greatest TI is the Inspire.
Okay, yeah.
And it's significantly different than the TI-84 or the TI-89.
I think the 84, yeah, that's the one.
Okay. The 84 is what a lot of districts use. The Inspire is a little bit nicer, but it really requires a new learning curve also. A lot of people don't like going from the TI-84 to the TI Inspire because it's just kind of it's like a different operating system. It's like going between Apple and IBM.
Yeah.
But if you were to graph this function on any calculator, you wouldn't see this hole. Why? Because that hole is infinitesimally small. In other words, it's there. X can never be 1, but a graph wouldn't show it because it would be too small to show up. So if I were to pull up, are you familiar with Wolfram Alpha?
And what was the first term?
Wolfram Alpha.
No, I've never heard that.
It's an excellent online program. Let me just point it out to you because you might find it really handy for calculus. It's called a database, a computational database. But if I put in the function that I just had there, x squared minus 1 divided by x minus 1, it will do all kinds of cool things. It'll graph it. Notice that it graphs it as a straight line and does not show the hole that's right there.
Yeah.
And your graphing calculator would not show that either. But this will do pretty much anything that any calculator will do. And it's free. In other words, you can go to Wolfram Alpha and any function that you want to graph, it'll find the zeros automatically for you. It'll do the derivative and the integral. It's a wonderful program. It'll find the roots. All of the things that you would have to do manually on your TI-84 or even the TI-Inspire, this will do frequently automatically for you. The biggest thing is finding the zeros. The zeros are usually what's tough. If you have like a cubic or a quartic or even a quadratic, and you put it into Wolfram Alpha and it'll give you the zeros without you having to go through the trace process, which you have to do with those graphing calculators.
Yeah.
Okay. Does that help explain the difference between vertical asymptotes and holes?
Yeah.
Okay. What else do we want to cover tonight? You had limits?
Yeah, we had limits. We had a quiz on, or like a mini test, I guess, just yesterday.
So what would the limit of this thing be as x goes to 1?
2.
Correct. In other words, you factor it first, change it to x. In other words, the first thing you do when you do limits is to always just substitute.
Yeah.
Problem is that when we substitute 1 for x, we get 0 divided by 0. And we don't know what that limit is, 0 divided by 0. So you generally have to factor or do something to the rational quotient in order to, in other words, after we factor it, it becomes that. And now when I plug in x equal 1, it goes to 2. So it's a piece of cake.
Yeah.
And that's generally the problem with limits. In other words, there's no problems with limits if you have a number divided by, what's the limit of that?
Does not exist.
Right, or infinity, either one.
Yeah.
Does not exist or infinity. If I have the limit of this,
It'd be 0.
okay. So anything that is not 0 divided by 0 is a piece of cake. It's either going to a number, it's going to infinity, or it's going to 0. So the only limit problems that are any fun at all is when you have 0 divided by 0. What's the limit of this?
1.
And they kind of give you that one without proving it. I presume they didn't prove this to you. They just told you what it was.
Yeah.
And the reason is that the way calculus is taught, they have this thing called, have you ever heard of L'Hopital's rule?
No.
Well, they teach that about halfway through the calculus course. And what L'Hopital's rule says is that if you have 0 divided by 0 or infinity divided by infinity, you can solve the limit by taking the derivative of the numerator and taking the derivative of the denominator. Have you gotten to derivatives yet at all?
No, not at all.
Not at all? Okay, well, the derivative of sine is cosine, and the derivative of x is 1. And now, if I substitute x equaling 0, I get 1. And that's why the limit of sine x over x is equal to 1, is because somebody used L'Hopital's rule to come up with that. But they got to teach one before the other, and they can't teach you L'Hopital's rule without teaching you this, and they can't teach you this without teaching you L'Hopital's rule. So they give you this as a given, and the same way that they give you this as a given. What's that as theta goes to 0?
0.
I didn't mean that. I meant this.
Is it 0?
Still 0, yeah. And those are the two that they give you. In other words, this would be 0 divided by 0, also, if I use direct substitution. But it's useful to study limits knowing what these two things are. And yet you can't really know what those two things are until you get halfway through calculus, unless they just tell it to you. All right. Have you had slope of the tangent line yet?
No, I don't think so.
That's coming up very, very shortly for you. So let's talk about it. Unless you have specific problems that you want to go over.
No, we can do this.
Okay. If I draw y equal x squared, parabola, and I want to know the slope of the tangent line when x is equal to 2, slope of the tangent line, prior to calculus, the only thing you knew how to do was to calculate the average change. In other words, I could tell you what the change of the tangent line is going from 1 to 2. It would be the slope of that thing. So it would be the rise over the run, right?
Yeah.
But if I want the instantaneous slope, at that point right there, I don't have any algebra that allows me to do that. And this is the difference between calculus and precalculus, is this concept of limits. If you had to define differentiation in 3 words only, it would be, or 4 words, it's instantaneous rate of change. Well, if I want to find what the instantaneous rate of change is, and I use rise over run, I've got a rise of 0 and a run of 0. So I don't know how to calculate it using the traditional methods for algebra. So here's what we do. We start, instead of the tangent line, we start with a secant line that goes, let's take some distance called h, and I can figure out the slope of that secant line. Let's call this, instead of y, let's call it f of x, because f of x notation is much more useful when you get into calculus than y notation is. What is the slope of that secant line? What's the rise? The rise would be f of, would that not be the rise?
Yeah.
In other words, this point right here is f of x plus h, and in this case, x is 2. But this point right there is f of 2.
Yeah.
And what's the run?
The run would be 2h, or 2 plus h.
2 plus h minus 2, or just h, right?
Yeah. Yeah.
Okay. So the whole thing here is that rise over run ends up being, if I were to take the limit of this thing as h goes to 0, and notice that as h goes to 0, this point here goes down the line, gets closer and closer to this point here. And so if I take the limit of that function as h goes to 0, I will have the slope of that tangent line. In other words, the slope of the tangent line is the limit of the secant line as it approaches the tangent line. You can kind of think of it as being, the way I've drawn it, it's a little hard to see, but if I start with that secant line, and then I start letting h get smaller and smaller, that becomes my secant line, and then that becomes my secant line, and pretty soon h is down here, and that's my secant line, and as h gets to 0, I just have a point. But my secant line will be a tangent line. And that will be the instantaneous rate of change of that function at that point. And in fact, the limit definition for instantaneous rate of change is f of x plus h minus f of x all over h as h goes to 0. That is the definition of first derivative. So, let's talk about the function x squared. We'll say f of x equals x squared. So let's figure out what the first derivative of x squared is. What the derivative function is. Well, what's f of x plus h? So I'm going to have the limit as h goes to 0. What is, I don't mean to say that, that goes here. First derivative equals the limit of that. So what's f of x plus h with regards to our function?
2 plus h?
Well, no, I haven't. I know I started this out saying evaluated it at the point 2, but this is more general. This is going to allow us to evaluate the first derivative at any point x that I want. In other words, I'm going to come up with a function that is the first derivative of x squared. So I need to start out with f of x plus h is x plus h squared. In other words, I take whatever's in the parentheses and plug it in for x. And then I'm going to subtract f of x, which is just x squared. And I'm going to put it all over h and take the limit as h goes to 0. Well, if I do that, now it usually comes down, once you get to this step, the rest of it is just kind of, it's not hard algebra, but it can get hard. It can get pretty hard. First of all, I have to expand that. What's x plus h squared?
X squared plus 2xh plus h squared.
What's going to happen every time here is that everything in the numerator without an h is going to cancel out. Then I'm going to factor an h out. So the numerator becomes h times 2x plus h divided by h, taking the limit of that as h goes to 0. Well, that h always cancels with that h. What's the limit of 2x plus h as h goes to 0?
H.
2x. In other words, this.
Oh, oops, I flipped.
That's okay. This goes to 0, so it just becomes 2x. So the first derivative of x squared is 2x. In other words, if I go back and I want to evaluate the slope of the tangent line at any x, I know that the slope of the tangent line is 2x. So my slope of the tangent line there would be 2. That would have a slope of 2. If I go to the point 2, the slope of that tangent line is 4 because it's 2 times x. And if I go back to 0, the slope of the tangent line should be 2 times 0 or 0, and it is. It's horizontal. If I go to minus 1, the slope of that tangent line is minus 2. So, based on this definition, you can come up with a function that represents the slope of the tangent line, or the first derivative. And then, whatever point you want to figure out, you just plug it in for x. So this is extremely robust here. The algebra can get a little complicated. Let's do a little bit harder one. If I wanted to figure out the derivative function of that right there. Remember the limit definition. The derivative function, and a lot of different, I don't know what you've had in the way of notation, but this sign right here means first derivative. So if I want the first derivative, that's going to be the limit of f of x plus h minus f of x all over h as h goes to 0. Well, let's fill it in. What's f of x plus h?
1 over x plus h.
And then I'm going to subtract f of x, which is 1 over x. I'm going to divide it all by h. Now here's where the algebra can get a little complicated. The next step here is to combine your two numerators. How do I do that? What's 1 over x minus h minus 1 over x?
X plus h over x times x plus h.
And if we finish this algebra here, notice the x's go away from the numerator, and I end up with minus h over x times x minus h all over h. Okay? So that's f prime. That's the first derivative. And I can simplify that. If I flip the denominator and multiply, I end up with minus 1 over x times x minus h. What's the limit of that as x goes to 0? As h goes to 0.
Negative 1 over x squared.
And that is the first derivative of 1 over x. Now, this is the hard way to do derivatives, I should add. Unfortunately, it's the way virtually every calculus class starts out, differential calculus, is once you get through limits and continuous functions, the next thing you're going to do is this. You're going to have to find the first derivative based on the limit definition. After that, after they torture you with doing all of this tough algebra, then they give you 4 rules that make it very easy to come up with first derivative. They're called the power rule, the product rule, the quotient rule, and the chain rule. And we can talk about them briefly. They're pretty simple, really. If I want the first derivative, y prime, then it's the exponent down in front, and then I take away 1 from the exponent. In other words, it's this. If I have x to the nth power is my function, then the first derivative is always n times x to the n minus 1. So if I had, say, y equals x cubed, then what's y prime going to be?
3x squared.
That's the first derivative. And notice how much easier it was using what this is called, which is the power rule. And then they teach you the product rule and the quotient rule, all of which are far easier than using the limit definition to come up with first derivative. But unfortunately, they are almost certainly going to start you out with the limit definition and make you figure out how to come up with derivatives based on the limit definitions of first derivative. And that's just ends up being a lot of, no matter how complicated the function is, it's just hard algebra is all it is, going through the limit definition. Whereas the product rule is really easy. Or not the product rule, the power rule. And furthermore, you can take second derivatives. If y prime is 3x squared, y double prime is the first derivative of this, which is 6x. And I can take third derivatives. If I keep going, what's the derivative of 6x?
Just 6.
And what's the fourth derivative of 6? Or fourth derivative of x cubed, really? Derivative of any constant is 0.
Okay.
Okay? And kind of the way you can think about that is if I plotted y equals 6, it's a horizontal line, right?
Yeah.
Well, what's the change of slope of a horizontal line? 0 the whole way. The slope at any point on that line is 0. And remember always that that's what derivatives are. It's the slope at that point in time. In other words, if I have a function that looks like this, I might want to know what the slope is at this point, right there. Well, that would be the slope of that tangent line. But more importantly, what I know about this function is what? What is the slope there and what is the slope there?
0.
So if I had a function and I wanted to know where this local maximum point was or where this local minimum point was, I would take the first derivative of the function, set it equal to 0, and solve. And that is probably the most practical application of differential calculus. Is it allows you to solve for maximums or minimums of functions. Because you will always find, have you gotten to local extrema yet?
No.
No? All right. If I look at this function between that point and that point, the absolute minimum is right there, and the absolute maximum is right there, right?
Yeah.
But it's frequently very useful to know local minimums and local maximums. This is called a local maximum. It's not the maximum of the function, but in this particular domain, it's the maximum in that domain. And this is a local minimum. And all that means is that a local minimum has points to the left and points to the right that are both above my minimum. In other words, whatever that point is right there, I've got points greater than it going to the right and to the left. And up here, I have points less than it going to the left and to the right. And these are what we frequently are trying to calculate, is where does the minimum and the maximum occur on that function. And that's also coming. So right now you're talking about continuous functions. What's basically the definition of continuity?
Like there's no breaks in the graph or holes. It's one.
Yeah, the layman's definition is that you have to pick up your pencil to draw it. If you can draw a function without picking up your pencil, then it's continuous. I can draw that without picking up my pen. If I'm drawing a hyperbolic function, this would be y equal 1 over x. I can't draw that without picking up my pen. So it's not continuous through 0. And clearly we can see why. It's because x can never be equal to 0. So it's not continuous at 0, but it would be if I wanted to list. Do you do intervals notation?
No, I don't think so.
If I wanted to write the domain of this function, the domain would be minus infinity to 0, can never be 0, in combination with 0 to plus infinity. Excuse me, this is a parentheses also. You always have parentheses next to the infinities. But this would tell you my domain. In other words, x can be anything from minus infinity to 0 or anything from 0 to plus infinity. The only thing it cannot be is 0. Sometimes you'll have things like this. a piecewise function. And let's make this 2. Let's make that 4. And let's make this point right here 1. And we'll call this function f of x. What is the limit of f of x as I approach 1 from the left? You've had left and right side limits?
Yeah.
Okay. What is the limit as I approach 1 from the left?
2.
What is it as I approach 1 from the right?
2.
What is f of 1?
F of 1. 4.
Uh-huh. In other
4.
words, the
Okay.
value of f at 1 can be different than the limit
Yeah.
as you approach 1. You've undoubtedly learned that the limit only exists if it's the same going from the left or the right. Let's go back and look at this function again. What's the limit as I approach x equals 0 from the right?
Infinity.
What's the limit as I approach it from the left?
Negative infinity.
Does the limit exist?
No.
It does not. No matter what it is, it does not exist if they don't approach the same thing. However, if I change this function just slightly and make it y equal 1 over x squared, now what's the function as x approaches 0 from the right?
Infinity.
From the left?
Infinity.
Therefore, it does exist. I'm not sure what I can say it is, but it exists because it's the same from the left as it is from the right. So it would not be appropriate to say does not exist for that one. I would answer this one infinity. That's the limit. But you can actually find some calculus books that will tell you this one doesn't exist either, because a lot of times they will use the word does not exist synonymously with infinity. In other words, back in Algebra 2, they wouldn't say that 1 over 0 is infinity. They would say it does not exist, right?
Yeah.
But in fact, it's actually infinity. It's just that they don't like to give you the impression in Algebra 2 class that infinity is a number. It's not. Infinity is growth without bound. So to say that the limit of this is infinity is not quite right either. You could say the limit approaches infinity, and it does exist. But it's different than that function there. This function here, the limit does not exist, merely because the limit from the left is not the same number as the limit from the right. But that other one is a bit of a tricky one. And what if the function looked like that, like this? And this is 1/2. So as x approaches 1 from the right, what's the limit of f of x?
1/2.
And from the left,
2.
what's the limit of f of x as it approaches 1?
does not exist.
Correct. And at the same time, f of 1 is equal to 4. So what its value is at that point is not really very critical to what its limit is. However, if you are looking for a more official definition of continuity, this is it. For something to be continuous, the limit from the left has to be the same as the limit from the right, and it has to equal what it is at that point. Okay? In other words,
Okay.
this clearly is not continuous. We can see that because we have to pick up our pen to draw it. But mathematically speaking, it's not continuous because the limit at 1, first of all, doesn't exist. But even if it did, it would not be equal to f of 1. And if f of 1 is not equal to the limit at 1, then it's not continuous. So, do you have a calculus text? Son?
Do I have a calculus? What?
Do you have a book? A calculus book? Just curious if it's the same one I have.
Yeah, I do.
Who are the authors of it? Is it calculus of a single variable?
I'll have to go get it from upstairs.
Okay. I should do that because it might be a little easier for us to work together if it's the same book as I have.
Okay, I'll be back in like a minute.
Okay.
Okay, the authors of my book is Larson, Hostetler, Edwards.
Okay, good. And it's called Calculus of a Single Variable. What edition?
Eighth edition.
That's exactly the book I have. Cool.
Okay.
Cool. So, and your inside page gives you all kinds of derivatives and integral tables. Is that on yours? If you open up the first?
Yeah.
Okay. Those come in handy, incidentally, whenever you're trying to memorize derivatives, because every trig function has a derivative. You'll notice I said the derivative of sine was cosine. Let's talk about that for a second, because that's kind of interesting. How could the derivative of sine be cosine? Well, hold on. There's sine. When I say the derivative of sine is cosine, it means that if I go through here and plot all of these slopes and then draw a second chart below it, guess what I get?
Cosine.
Cosine curve. In other words, notice that the slope right there is 1. The slope up here is 0, which is this 0 point right there. The slope right there is -1. That would correspond with this point down here. And then again, I have a 0 slope. I didn't quite draw this correct. I would want to draw it more like, I would want to end it here. So it kind of like that. It's a little bit more accurate, I think. But when you talk about a first derivative function, that's exactly what you're talking about. Is if you were to take the original function and figure out what the slope of the tangent line is as you move along the x-axis, and then you graph that function down below, that's exactly what you're going to get. This would be f prime of x, and this would be f of x. In fact, let me do this. I have a really good thing that's not from that book, but it's still really worth looking at. Let me think how I'm going to find it here. Where is it? It's in my calculus. This curve right here. This is a terrific curve to figure out first, second, and third derivatives. And this is coming up pretty quick for you also. This is the original function, x cubed plus 3x squared minus 9x plus 3. Graphed below it is the first derivative. Notice that if I apply that power rule, I get 3x squared plus 6x minus 9. And notice that there's some really key things you need to know about derivatives. One of them is if the original function is increasing, its first derivative has to be positive. Notice the original function is increasing from that point to that point. Its first derivative is positive from that point to that point. It's decreasing, but it's positive, right?
Yeah.
If the original function is decreasing, the first derivative has to be negative. In other words, between that point and that point, my first derivative is below the x-axis, so it's negative. Finally, when the original function starts increasing again, its first derivative goes back into positive territory. So that's the first rule, is that if a function is increasing, its first derivative is positive. If a function is decreasing, its first derivative is negative. And when a function is not either increasing or decreasing, like at that point there and at this point there, that means the slope of the tangent line would be 0, and its first derivative would be 0. So hence they draw these dotted lines to show you that, at this local maximum, my first derivative is 0. So if I was solving for that point, I would make that equal to 0. And then I could tell you what that point is and what that point is. The third curve is the second derivative. Plotted, the only difference between these three graphs are this is y prime, and this is y double prime. And all of the rules that relate first derivative to the original function apply when you're talking second derivative to first derivative. In other words, the second derivative is merely the first derivative of the first derivative. So if I look at the second and first derivative curves, well, those same rules have to apply. Wherever this thing is decreasing from there to there, my second derivative has to be negative, and it is. It's negative from here to here. It's then 0 when slope of that tangent line is 0, and it's increasing the rest of the way, and so my second derivative has to be positive the rest of the way. So don't know why this book does not have these in it, but I show this to pretty much anybody I'm tutoring calculus because it's so useful, because you're going to get to a point where they're going to give you a first derivative function and you have to go backwards and figure out what the original function looked like. And you do it based almost entirely on, is your first derivative positive? If it is, the original function has to be increasing. Is your first derivative negative? If it is, the original function has to be decreasing. And so forth and so on. And that can get to be quite the exercise when you have to do that. And you can do it given the function, or you can be given that problem given the graph. In other words, they might give you this graph and say, which is the original function? What does it look like? And you'd have to trace your steps backwards to get up to this. Because a lot of times in life, we don't have the original function. We have derivatives. I don't know if you know, but velocity is the first derivative of position, and acceleration is the second derivative of position. So you may not know what your position is, but if you know your velocity and you had a table of your velocity, let's say you're going to drive to New York City and you know what your velocity was at various points in time, you can trace that back and figure out exactly how much distance you've covered. All right, let me look in this book. Do you know what, are you on chapter 1 still? Or you must be on chapter 1.
We're still in chapter 1.
1.4 is continuity and one-sided limits. Okay? And you can see what chapter 2 starts out with. The derivative and the tangent line problem. If you go to page 96, you will see what I was attempting to draw. Actually, page 97. You see the secant line in 97 at the top?
Yeah.
And you see that c plus delta x and f of c plus delta x. And then finally it gives you the slope of the secant line is f of c plus delta x minus f of c all over delta x. And finally at the bottom of the page it gives you the official definition. Actually on page 99 is where you get the official definition of first derivative. And that's what I was giving you. Only delta x is the same as h. The delta notation merely means that it's a very small number, never zero, but approaching zero. Okay?
Okay.
All right. Well, that's good that we have the same books, because if we do another session and say you have homework that is at the end of chapter 2, well, you don't need to send me anything by email. I can just go to my book and I'll know what your homework problems are.
Yeah.
So it'll be useful for that. Yeah, this sounds like probably a pretty good place to stop. I've been kind of bouncing around over a lot of subjects here just because I wasn't quite sure where you were at, but now I will be. You just have to tell me where you're at in the chapter and which part.
Okay.
Okay? Side, let's see. Can I get, maybe I have, your mom gave me this website.
Yeah.
This is your school district website. Is this useful to me at all? Do you ever need this, or are going to use this during tutoring?
No.
Yeah, I didn't see anything on here that it looked like it was useful. But we don't need that anyway because we've got the same book. The only thing that I need, here, let me see if I have it. Let's see if I have an email address for you. Because I record all of these sessions and I need to send you a link. I don't have an email for either you, your sister, or your mother. Can you give me one?
Yeah, I can give you my mom and my email. Or you just want one?
Give me your mom's email, and I will send the link to the recording of this session to that email, and then she can forward it to both you and your sister.
Okay.
And
can you?
Yeah. What's your mom's email?
Okay. K1.
Okay.
SIDDI QUI @yahoo.com.
Let me repeat that. K1 SI D as in David, D as in David, IQUI @yahoo.com.
Yeah, that's good.
Okay. And it actually takes my computer a few hours to process this recorded file. So it's never available until like the next morning.
Okay.
Just kind of keep that in mind in case. A lot of people like to schedule tutoring sessions the night before a test, but if you do that, you won't have a chance to review it before your test. Whereas if you schedule a tutoring session 2 nights before your test, then the next day you'll have a recording of the tutoring session that you can review. Right? And you can, of course, it's a YouTube format, so you can fast forward it, pause it, do anything you want with it. But it's useful for hard, complicated subjects like calculus.
Okay, so if I had a test like coming up and I wanted to get in a session with you, could I email you about it and we could do something maybe 2 nights before?
Yeah, absolutely.
Okay.
You or your sister or your mom can always contact me and find out if I have available time. And if I have an available time, we can certainly do a session.
Okay.
Okay. And okay. So, Saad, I will hopefully speak with you again, and good luck in your calculus, and I hope I've been of some help.
Okay, thank you.
You're welcome. Bye-bye. To log out of Gotomeeting, you just need to hit the X at the upper right from the control panel, and that'll log you out of the meeting.
Okay.
Okay?
Okay.
All right. Bye.